welcome back. In the last lecture, we obtained certain very interesting results. We obtained the expression for the propagator of the harmonic oscillator and the free particle using the path integral approach. Before we proceed further, it would be opportune at this point to discuss the equivalence of the Schrodinger formalism and the path integral formalism. So, let us start with that today, and then we will proceed to work out the time ordered products and the expectation value for the time ordered products in the path integral framework. So, that is the agenda that I have for today. Time permitting, I will also discuss a little bit more about the features, the properties, the nuances of the path integral, but let us start with the equivalence between the Schrodinger and the path integral framework. Now, the first thing is that the Schrodinger equation is a differential equation. So, being a differential equation, it relates to time evolution, or it provides an expression for the time evolution at the infinitesimal level. In other words, it gives you the infinitesimal evolution in terms of time and in terms of the wave function. So, that is what we have to keep at the back of our mind when we try to establish the equivalence. The Schrodinger equation is a differential equation, and therefore, we have to deal with infinitesimals. Now, as far as the path integral framework is concerned, the expression for the evolution of a state from t equal to 0 to a small t equal to delta is given by the expression in the green box, that where this k q dash delta is the transition amplitude, and this expression gives you the time evolution in the path integral framework. Now, for the transition amplitude, and the expression that we have derived for the transition amplitude in the path integral framework is the first equation given on your slide. This is what we obtained in the previous lectures for the Feynman's path integral in configuration space. For infinitesimal time evolution, obviously this equation simplifies a bit, and we have to retain only the portion that is there in the green box. For I reiterate the fact that the expression in the green box holds for infinitesimal, for very small time evolution, where the evolution time is very small. Now, substituting the transition amplitude 2, that is what we had in the previous slide, this green box expression, this is expression 2. In the expression 1, which we have originally for the time evolution in the path integral framework, we get the expression which is here in the green box right at the bottom of your slide. And so, this is what ultimately we have to manipulate, and we have to put it in a form which is compatible or which is equivalent to the Schrodinger equation. So, this is what we have, from the previous slide. We to introduce compatibility of notation, or convenience of notation rather, we introduce eta as the expression q dash minus q, and in terms of eta we write down, obviously the integration element changes from dq dash to d eta, q being stationary, and we get the expression which is there in the green box on making this substitution. Now, let us consider this exponent, the exponent of the exponential, exponent e to the power the curly brackets I m upon 2 h delta eta square minus I delta h v q plus eta by 2. Let us look at this expression. Let us look at the behavior, the qualitative behavior of this expression. Clearly, since delta is infinitesimal small, large values of eta would result in this integral, this whole expression, this exponential being showing rapid oscillations, and as a result of which these rapid oscillations, what will happen is that the contributions overall contributions will be nearing 0. So, the important or the relevant or the dominant contributions are going to come from the area. Now, we expand the potential function also the exponential of the potential function to first order, which is because we are dealing with infinitesimals. So, expansion to first order is adequate for our purpose, and that is precisely what we have done in this slide. We have expanded the exponential of I delta upon h bar v q plus eta by 2 as the prefactor remains as it is, and we have expanded the exponential as I 1 minus I delta upon h v q plus eta by 2, that is the expansion of this exponential to first order, plus of course higher order terms would be there. Now, let us expand the wave function as well. When we expand the wave function, this is what we have, the red box contains the expression from the previous slide of the expansion of the potential, and now we expand the expression in the green box. When we expand the expression in the green box, we get the corresponding expression in the green box in the bottom equation, in the last equation. This green box gives you the expansion of psi q plus eta comma 0, the Taylor expansion around q comma 0. This is simply the Taylor expansion of q psi plus eta comma 0 around q 0, nothing more, Taylor expansion, and the rest is same. Of course, we have also expanded this potential function v q plus eta by 2 in terms of a expansion, Taylor expansion v q plus higher order terms. Higher order terms in eta, and this higher order terms in eta would also be multiplied by delta. So, it would be higher order terms in delta and eta, which have simply written as order delta square. Now, all we need to do is to simplify the expression given in the red box and to ignore or to eliminate expressions of higher orders. That is precisely what is done. If you look at the expression in the green box, it is a simple multiplication of the two expressions in the brackets, and what we get is the residual part. Of course, the integral, the rest of this stuff remains as it is, and the exponential I m upon 2 h delta eta square also remains as it is. The first term, this whole thing is to deal with basically the potential term, the simplification of the product of the potential term and the wave function. Now, we do the Gaussian integrals. If you look at this carefully, this is nothing but a Gaussian integral. The first term exponential I m upon 2 h delta upon eta square is a Gaussian integral. We can do it. Of course, we need to adopt a regularization parameter, introduce a regularization parameter delta here, because the integral is oscillatory. So, we introduce a regularization parameter delta, and so on simplification this is what we get. Similarly, we do the integral of eta and it gives us 0, eta exponential I m, this expression gives us 0, and the expression eta square exponential I m upon 2 h delta eta square integrated over the entire spectrum gives us the expression on the bottom of your slide, right hand side. Now, we substitute all these values into our original equation. This was our original equation. The top equation was the original equation that we obtained by simplification, and we simply substitute the integrals now. This is the integration has now been done, and the integrals have to be substituted. The integral of exponential I m upon 2 h delta eta square, then you have eta into this exponential, then you have eta square into this exponential, eta square into this exponential, this term. So, all these integrals have been done in the previous slides, and we make simple substitutions. On substituting all these expressions here, what we end up with is given on the next slide. It is here in the green box. We get psi of q comma delta is equal to psi q comma 0 minus this whole expression. You take psi q comma 0 to the left hand side, you get this expression which is there in the green box right at the bottom of your slide. A simple algebraic manipulation, otherwise there is no other mathematical operation than algebraic manipulations, and we end up with the expression that is given at the bottom of your slide in the green box. Now, if you look at this, if you look at this in the infinitesimal case, if you take the limit delta tending to 0, transfer the, first of all transfer the prefactor here, transfer this prefactor to the left hand side, and then take the limit delta tending to 0, it simply turns out to be a partial derivative of psi with respect to time, and that is precisely what is here. Of course, the prefactor becomes I h bar, as you can see here. This minus I upon h bar can be written as 1 upon I h bar, because minus 1 is the I square. So, it can be written as I upon I square h bar, that is 1 upon I h bar. This goes to the left hand side, it becomes I h bar, delta goes to the denominator. We take the limit delta tending to 0, and we get the I h bar as the prefactor, and then the partial derivative of psi with respect to time, and that gives us the left hand side. The right hand side is clearly what we wanted already. If you look at it, it is clearly in the form that we want. You ignore the higher order terms and you get the Schrodinger equation. So, starting from the path integral framework, we have been able to arrive at the Schrodinger equation, and that shows clear cut correspondence between the path integral framework and the Schrodinger equation. So, this is an important nuance, important attribute of the path integral framework, that there is a correspondence, clear cut correspondence between the non-relativistic path integral and the non-relativistic Schrodinger equation. Let us now turn to the development of the formalism of the path integral, which we will be requiring for the application to quantum field theory. What we do now is to determine the matrix elements of the coordinate operator q hat t in the path integral framework. In essence, what we want to determine is given on your slide. We want to first determine the first expression, the operator q t I at a particular point in time t I, sandwiched between the final state and the initial state, and we also want to determine product of such operators sandwiched between the final state and the initial state of the physical system, quantum physical system in the path integral framework. That is our exercise. So, let us start with the first problem. The first problem is we want to determine this expression, where t I is obviously some time interval or some point in time between the initial time and the final time, the time of the starting of the time of this evolution and the up to the final evolution of the system. T double dash is the final evolution of the system, T dash is the initial evolution starting time of the system, and T I is somewhere in between, any arbitrary point in between at which we want to observe the matrix element, determine the matrix elements of the operator, coordinate operator q, which is obviously time dependent in the Heisenberg framework. Now, what we do is, as we have been doing, in fact, we do a time slicing. We discretize the timeline into a lattice, into a grid, and in the form that is given in your green box. The starting time is arbitrarily named as t1, and then t2, t3, these are various points on the timeline. Now, the timeline consists of a lattice of points, a grid of points t1, t2, t3, but while doing so we have a caveat in mind. We have a something at the back of our mind. That something at the back of our mind is that one of these time points, one of these discrete lattice points should coincide with the T I at which we were to determine the matrix elements of our given operator. In other words, one of these, you see, this is a partition of the timeline. Obviously, we have discretion of how to introduce or how to implement this partition. We can make it as fine as we desire. So, we ensure that the partition is fine enough that one of the points of this partition, that is one of the lattice points, one of the nodes of the lattice coincides with the T I that we want to determine, at which we want to determine the matrix elements of the coordinate operator. This particular T I, this T I should be one of the nodes, one of the points on the lattice or on the grid in which we have converted the timeline. So, having done that, now and that is obviously possible, because we can partition our timeline into as fine a grid as we like. So, that being the case, what will happen is, as you will see later. So, I will come back to it in a minute, but before that, what we do is the standard procedure like we had done earlier when we worked out the path integral. We introduce position complete sets of position states. We introduce complete sets of position states corresponding to each of those lattice points, each of those grid points, as precisely what we have shown in the second integral, the bottom equation. Now, the important point is here, because this complete set of states has been introduced, and in the moving basis, of course, and one of the grid points corresponds to our T I. Therefore, at T I also we shall have a complete set of states, and we shall have some kind of an inner product developed in this form, a sandwich developed between Q T I with Q I, the state Q I T I on the right, the ket state, and the dual state Q I plus 1 T I plus 1 on the left. This is precisely what we will get because of the manner in which we have done the partition. Now, that being the case, now this operator Q T I, will act on the state that is on the right, and because you see this state Q I T I is a eigenstate of this particular operator Q at T I, and therefore, when the operator operates on this particular state, it returns the eigenvalue of the operator. So, now the eigenvalue would be a number, and therefore, the net effect of this would be to replace this operator Q T I with a number Q T I, which represents the eigenvalue of that operator because of the operation of this operator on its own eigenstate. So, in a nutshell, what we have done is, just to recap, we have introduced complete sets of states at various time points in the corresponding to the grid, and because one of the time points on the grid coincided with the point in time at which we were to determine the matrix elements of the operator, this particular phenomenon happened, which enabled us to substitute the operator with its eigenvalue. So, what has happened now is, as you can see here in the red box, this operator Q T I acts on the state Q I T I, and we get the eigenvalue Q T I. Note, this Q T I is without the hat, showing that it is a eigenvalue, it is a number, it is not an operator, and therefore, once this phenomenon is done, this Q T I can be taken outside this whole sets of states, and we simply what we retain is nothing but the original path integral with the expression QTI sandwiched in between as you can see in the green box. The important thing is QTI is now a number. So, you can put it here because it is no longer an operator, and why it is not an operator? Because of this particular process whereby the operator is acting on its own eigenstate and returning the eigenvalue. So, that is how this is the expression, the green expression is the expression for the matrix elements of Q operator QTI in the in between the initial state and the final state. Now, we develop this formalism further. We now look at the time ordered product operator product of two operators, time ordered product of two operators. Let us assume that we have got two operators, say position operators, coordinate operators QTI and QTJ. Let us for the moment assume that Ti is greater than Tj. Let us assume QTI is greater than Tj. Now, as in the previous case, we do the same exercise, we introduce position complete sets of position states, but before we do introduce complete sets of position states, we discretize the timeline as we did in the previous case. Again we ensure that the partitions that we have formed of the timeline, the lattice that we have formed of the timeline is such that we have nodes corresponding to Ti and Tj on the lattice. In other words, these points and these time points corresponding to some nodes on the discretized time lattice or the discretized grid that we have constituted. So, that being the case, because we are assuming Ti is greater than Tj, or therefore, what will happen is Ti will appear to the left and QTI will appear to the left and QTJ would appear to the right as per the ordering of the grid of the lattice. So, again what will happen? We will get a situation which is similar, absolutely similar to what we had earlier. We will have the operators QTI acting on its eigenstate and operator QTJ acting on its eigenstate, because remember these two correspond to nodes on the timeline. So, both these operators will act on their respective eigenstates and return the corresponding eigenvalues. The net effect is that we can substitute the operators by the corresponding eigenvalues, and that is precisely what is done in the green box. The rest of the exercise remains absolutely same, and we have the expression for the product or for the matrix elements of the ordered product. Which ordered product? QTI, QTJ sandwiched between the initial state and the final state. The matrix elements of this particular ordered product of operators is given by this expression. Remember, QTI and QTJ now in the green box are not operators, they are numbers. So, they can commute, you can as well write them in the other order, it does not make any difference at this moment, but we will come back to it in a minute. Now, the important thing is suppose this condition Ti is greater than Tj. We started with the condition, if you recall, we started with the condition that Ti is greater than Tj. Just look at this in the violet box, Ti is greater than Tj. Now, suppose we reverse this condition, what happens? Now, if you reverse this condition, then what will happen is that this process that we were able to implement will not be possible to implement this particular process, because in implementing this particular process we have assumed a sequencing of the states of the timeline rather, so with the lower with the earlier times being to the left and the later times being to the right, timeline moving from the I am sorry earlier times to the right and later times to the left. As you can see here also, T I is appearing to the left and D j is appearing to the right with T I greater than T j. So, in other words, you are moving from the right to the left in terms of the timeline. The gridding or the lattice numbering is in that form. The structure of the lattice is such that the nodes, initial nodes or the earlier nodes are to the right, and as the node number or the node sequence increases as you move towards the left. So, this has to be preserved in order that this particular phenomenon takes place and we are able to replace the respective operators with their eigenvalues. This particular ordering has to be respected. Otherwise, you cannot do it. For example, if Qj was put to the right and Qj was put to the left and Qi was put to the right, this kind of placement of the eigenstates would not have been possible, and as a result you could not have replaced them with their respective eigenvalues. So, this ordering T I greater than T j and the ordering of the operators Q T I and Q T j must be respected. The later operators must be to the right and the earlier operators or the earlier operators acting at the earlier point in time must be to the I get mixed up, I am sorry. The later operators must be to the left and the earlier operators must be to the right. You start with the earliest operator at the right hand side, and as you move towards the left, time is supposed to increase. Time is supposed to increase from the right to the left, and if T I is greater than T j, it means what? It means that Q T I is occurring after Q T j, and therefore, Q T I would be placed to the left of Q T j. So, the important thing is, if T I were to be less than T j, then this framework would not work. In other words, putting it the other way around, the path integral framework of determination of these kind of matrix elements implicitly assumes a particular ordering. It assumes that the operator that is being placed first is earlier in time, placed to the right is earlier in time compared to the operator that is placed to the left, which is later in time. It implicitly assumes that, notwithstanding the fact that it is not explicitly mentioned, and if that order is not preserved, then the results would not be consistent. So, under the opposite condition, the calculation would not hold, since the path integral assumes an increasing ordering from right to left. Right is the lowest, left is the higher of the grid points in time. Right. So, the conclusions that I have already mentioned, the path integral automatically assumes a certain time ordering from right to left, as I said, right being the earlier, left being the later. The path integral expression involves the eigenvalues of operators, these are C numbers, as I said, and they do not involve any ordering. But within the, see, the point is, once you put it in the path integral, then the eigenvalues can do commute. The eigenvalues being C numbers, they do commute, but their commuting would not influence the order in which the original operators were taken. The operators must necessarily be taken with the earlier operator being to the right and the later operator being to the left. That has to be preserved, howsoever you may write those eigenvalues in the path integral. So, this expression can be generalized, of course, to a number of operators, and there is I mean it is a consistent framework. So, instead of having 2 operators, you can have a number of operators, and instead of writing time and again that Ti is greater than Tj, we simply have a time ordering operator placed in front of them, which automatically implies that the expression within the square bracket is to be understood in such a way that the earlier operator, whichsoever it is, the earlier operator is to be taken as the one to the right, and the later operator, whichsoever it is to be taken to the left. For example, if I write it this way, you do not have to explicitly see that Ti or Tj, you do not have to write them explicitly, Ti is greater than Tj. Even if Ti were less than Tj, then writing like this would ensure that Qti appears to the right and Qtj appears to the left when you do the actual calculations. Thank you. We will continue from here.